Alright, hello and welcome to the next lecture. This one's going to be about compression. It's going to be very interesting because we're finally going to use all these data structures, or at least some of them, that we've been building up. Like, we're finally going to see them in action. So this is a great example. I guess let's just get right on into it. The things that we're going to learn how to do is, the type of compression that is called HUFFMAN compression. So we're going to be building a fancy tree, and let's get right into it. So surely you have felt the need for compression at one point in your life. The usual problem is you have like a string, which you can consider a file to be a string, right? And you just want a tinier version of it. So you want your large file to become a little tiny file, and you want to be able to, this is compression, you also want to be able to decompress, usually, to the original file, okay? Let's put that inside the bounds of this PowerPoint. This is the original file that you want back, okay? So that's essentially the idea of lossless compression. And that's what we're going to be looking at today. So you don't lose the original file. It is the same one that you decompress. Okay, that's the idea. So you have used compression if you've used the internet at all. All the web pages are sent to you compressed usually, and that's probably the main way that you've been using compression all your life, but maybe not know about it. Maybe you are a fancy programmer who's working on a very small device where space is precious, so is computation time, and there are trade-offs that you have to make, and you want to store things in a compressed way. But still you want to regain the original file at the end of the day. Also, another very common way to do things is like images or video. So if you want to store any kind of video that is anywhere close to high quality and lasts longer than just a few seconds, you have to compress all of those frames, and that's called lossy compression, and that's not something we're going to talk about today. It looks very nice, but it's not the original file anymore, sadly. JPEG as well is a very good example of a lossy compression algorithm. The file gets smaller, but at the end of the day, it's not the same file that you're looking at anymore. Okay, that is motivation for compression, but let's have a real example now. So it makes a whole lot of sense to compress things because some things are more occurring than others. They occur more often in a certain type of file. So, for example, in text, like the works of Shakespeare or something, you're always going to have the vowels appearing a whole lot more often than the consonants. So, for example, take this sentence right here. There are 4 A's, 5 E's, 1 I, 6 O's, and 1 U, and that's already 30% of that data. Okay? So that's more than, I have a feeling it's more than 5/26. Okay, if it were average. Every character appearing just as often. That's much larger than that. Okay, so, and even more if you don't include spaces. Spaces are also very commonly occurring, maybe even more than vowels in some files. So that is the idea for ASCII. So that's files and compression. We like to compress things. You've made zip files a whole lot. Okay, so let's talk about one way to compress things, and it will be using this fancy data structure called a trie. So these are tries, and the reason that it's pronounced tries is because it's supposed to be, it was originally supposed to be pronounced trees, and just it's spelled differently, but then people started trying to differentiate it in speech from trees, okay? Just because we want to differentiate it from trees. And the original etymology of this word is it's the middle part of retrieval. It was originally supposed to be pronounced tree, but now we call it tries. Okay, that's the idea. And usually they hold strings. They can hold other things though, and the main operations on these tries are insert and search or retrieval. All right, so let's take a look at what a try is, because it's very similar to a tree. It is essentially a special kind of tree. Okay, so here are tries that hold words. Okay, this is the idea. You can store dictionary words in a try. And at the leaf nodes, you have data. Okay, some intermediate nodes also have data. Okay, and you can mark them especially. So here's one way to store like dictionary words, like maybe for a spelling checker. Like TO, that makes 2, you follow those paths. So each edge is a character. And they eventually build up words, all the chars together on a path, usually down to a leaf or close to a leaf, build up words. Okay, so one fun reason to use a try and store words like this is for auto-completion. So like you can be like, okay, the user has typed T and E. Let's figure out the most common one of these to autocomplete. Okay, that's the idea. If you store like frequency data, that's useful. Also spelling checkers, things like that. Technically, you don't actually store the words at the leaves. The word has already been built up from the path itself. Okay, so what you normally do is you just store on the edges or in the nodes themselves the letter that you're following. Technically, this could be considered a B edge. This could be considered an A edge. Okay, that's the idea. And so as you go to a root, you can mark when you have an actual, or as you go to a leaf, you can mark when you have an actual word. So like bat and ball are both leaves and full words, but do is a partial word that can be used to make more words, like doll or dork or dorm. So you can maybe flag those nodes. There's a special way to do that. You can just change the way that your node struct works, okay, with little stars on them. Okay, that's the idea. So that is tries in a nutshell. They're going to store words usually, and each edge stores a character. Okay. In our example here for Huffman compression, we're going to be using a binary try, which has on its edges are 0 and 1. And oh man, you might be thinking, and it is correct, hey, that's just a binary tree. All right. So the idea is that this binary tree will represent the data that you need to encode characters, okay? Represents an encoding of the characters, let's say. Represents a compressed encoding. So instead of, like, A is, you follow the path from the left, so it's 0. A is just 0. B is 1, 0. See that? 1, 0. And then C is 1, 1, 0. And D is 1, 1, 1. So suddenly, A is a lot less, it takes a whole lot less information to store A. It's just a 0 in your data, in your file. And then B is a 1, 0. Whereas C and D take up more space. So you can choose more popular letters, like A, which is a vowel. Okay? A popular character. So it's going to take up less space. A smaller bit string. Okay, so I think that's all I want to say for compression and tries, and now we are ready for Huffman coding. This is a example of compression. It is lossless, it is optimal in a certain sense, and the idea is when you put together a binary trie and you build it up using a priority queue, you get tiny heart, which is a compressed heart, I guess. You get compression, okay? That's the idea. And everybody calls the trie that you make a Huffman tree because it is the same as a binary tree, so we're just going to say it as a tree from now on. And the goal is, again, to shrink the average amount of information needed to encode some text. So normally, every char in C++ is 8 bits, 1 byte exactly. But some characters appear more often than others. So if we can make those more often appearing characters to take less bits, then suddenly we are in business. And that will give us compression. Now suddenly, the more frequent characters take up fewer bits, which means the overall file size is going to shrink. Unless it's like a random document. Okay, because there are patterns and we can exploit those patterns. Okay, yeah, I think that's all I wanted to say there. So let's go to the algorithm from the book now, and here's the idea. We're gonna, step 1 and step 2 are essentially all you have to do. The first step is to build a character frequency table. So you get the file that you want to compress ahead of time, and you can study it. Usually this is the case. You already have a file on your hard drive, so you can read it and discover some properties about it before you start compressing it. And so you'll just build a table keeping track of how often each character appears. And if I go to your book, they talk about that up here. Just build a frequency table, not too bad. And so for each character, you count how often it appears in a certain sentence. Okay, and this one they're doing apples and bananas. So notice that vowels. We love the vowels. So that's the frequency table, and they're going to use that frequency table to build this Huffman tree, which is secretly a binary trie. And you ensure that the characters that are used more often have shorter codes. So that is shorter paths to the leaf, to their leaves. Because each character in the trie is going to be stored at a leaf. Stored at leaves. Okay, that's all I want to say there. So the way that you build this Huffman tree is the fancy method. So you have this frequency table, and then you go and exploit it down here to take in the table, and you use this priority queue, and you pop off lower priority nodes, and suddenly you build up trees with them. Okay, so let's see here. So we count the frequencies, and we start with the least frequent characters, and we merge them into nodes. Okay? into a subtree. Okay, we make nodes out of them, we merge them together into a subtree. That's the idea. And then we keep track of the frequency that they have combined. And we just keep on repeating this process with a priority queue. And the priority queue keeps track not of frequencies of characters, but of subtrees. Subtries, I guess. And this might make no sense at all, but don't worry, I'm going to give you an example in just a minute after all these words. So your priority queue keeps track of frequencies of subtrees. You start with the least frequent, not characters anymore, but they start out being characters, the least frequent subtrees, and we merge them together into a new subtree, and we keep track of their combined frequency, and we keep going until the priority queue has just one thing left in it. So here's the idea. Keep on following this process. Keep extracting the nodes with the smallest frequency and building up the Huffman tree some more. As long as you have more than one subtree still. Once you have just one subtree, you have combined everything. There's no, there are no nodes that are outside of the tree. You're left with one big root node. And that's the idea. So that is my best English description of this, and it is a bit complicated. The idea is we're using a priority queue, we're keeping track of frequencies. The best way to explain this is to use an example. So I'm going to use a example from pop culture. We will use Among Us. All right, so we're going to build a tree for this example sentence, emergency meeting. So the first thing that we need to do is make the frequency table, okay? Dun, dun, dun. So we have to keep track of how often each character appears. And let's see, where do I want to do this? I think I might want to do this in a separate place so that I can put this somewhere else later. So we've got E's, we've got M's, we've got R's, we've got G's, we've got N's, we've got C's, we've got Y's, M is already there, E's already there, T's, I's, N's already there, and G is already there. Cool. All right, so how many E's in this sentence? We have 1, 2, 3, 4, 5. So that's our frequency table for E's. That's how you filled it. You're just going to iterate through. How many M's? 1, 2. Hopefully I get this right. I'm sorry if I miscount. It'll still be a good example if I do, though. R's, just 1 it seems. G's, 2. And N's, technically there's a space, but I'm not going to worry about spaces. N's, 1, 2. Feel free to fast forward. C is just 1. Y is just 1. T is just 1. And I seems to be just 1 as well. So how many characters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16. So let's make sure this is 16. 2, 4, 6, 7, 8, 9, 10, 15, 16, 17. Oh no, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, I'm happy. So that's our frequency table. Okay, now that we have that, we can use it to our advantage. So now we're going to build the tree very, very slowly by taking the two least frequent nodes and combining them. That's by repeatedly. So how in the world do we go from characters to nodes, you might ask? Well, the first step is to make everybody a leaf. Okay, if we go to this, the idea is we push a bunch of leaf nodes. So let me show you that process. So first we make everybody a leaf node, every character a leaf node, and push them into the priority queue. And all the nodes, they keep track of their frequencies, okay? So we'll repeatedly pop off the least frequent stuff, so it's a min heap, and combine those nodes. Okay, so here we go. I've got my frequency table. I've got now, I'm going to make a queue. I guess I'll just make this a blank slide. Here's my frequency table. The first thing I need to do is make my priority queue. Okay, so the priority queue, PQ, it's going to hold all these things. It's going to hold a bunch of leaf nodes at the beginning. Okay, so I'm just going to, I don't know, I'm going to draw it like this with everything all over the place, but just remember that it's ordered. Maybe I'll just put everything in a box. Who knows? They're all jumbled around. So you've got the E node with frequency 5. I should save that somewhere. Let me just put them outside for a second. E with frequency 5. We've got M with frequency 2. We've got R with frequency 1. We've got G with frequency 2. We've got N with frequency 2. We've got C with frequency 1. Y with frequency 1. And then T and I also with frequency 1. So this is our priority queue. It looks like this. And the idea is this priority queue is going to change as we build things up. So it's just going to be one big priority queue with subtree nodes inside of it. Okay, so right now we've just got a bunch of leaves which keep track of their frequencies. And this is what we did first. Okay, we made the frequency table. We put everybody as a leaf node into the priority queue. Hopefully that all makes sense. So that's what we did. And okay, we're ready. Let's keep going. The first thing that we're going to do now, just repeatedly, we're going to take the two least frequent nodes and combine them into a super node, into a subtree. All right, so the two least frequent nodes, it could be any of these four. Let's just go in the order that I put them last. So let's use T and I. Okay, doesn't really matter. So T and I will be chosen at random because they are the least frequent, and we won't order them when they're all the same. These are all ones. So we're going to put T and I together into a subtree. Okay, so here we go. T is a 1, I is a 1. We're going to put them together in a new subtree, and this node will have frequency, the sum of them. Okay, so 2. That is the idea. So now we have this node, and we put it inside the priority queue. Okay, and get rid of these two. We popped them. So now the priority queue is this whole thing with this subtree as well. This is one subtree now. Okay? The two least frequent nodes and combining them, and then pushing that new subtree back. Okay, so that's the process. And this is miraculously going to come up with a binary tree that is going to compress. Like, it's going to show us the shortest optimal codes for these characters, which is beautiful. All right, so technically this is the 0 side, this is the 1 side, right? So now, here are all my nodes. I'm going to pop the 2 least frequent ones now. And remember, the frequency of this entire thing is the frequency of the top node. So this has frequency 2 right now. Okay, it's a subtree. All right, so now I've got, 1 and 1 and 1 still. All right, I'll just pop these 2 now and combine them together. Okay, so I've got the C with frequency 1 and the Y with frequency 1. And we're going to combine them into a frequency 2 node. All right, that's the idea. Boop. And so now we've got a frequency 5 node, a frequency 2 node, a frequency 1 node, and a bunch of frequency 2 nodes, because we consider them together now that these have been, like, they're linked for life. They are chained together. Okay, so now we pop the 2 least frequent nodes, and oh man, now we have a bunch of options because we have all these 2s everywhere. I'll make it easier on myself and choose, like, how about the R and the N? Dun dun dun. Those are the initials of my dad. So we've got the R over here. Let's put them here. R1 and 2. Those are the 2 least frequent nodes. You could have picked any of the 2s, but you had to pick the R. And then the sum of those frequencies, the bigger node now, has frequency 3 because we've summed them together. Okay, so the R and the N go away. This is what it means to make a Huffman tree. We're building them up, slowly but surely. So now we find the 2 least frequent nodes because we pushed all these back into our priority queue. This is the entire priority queue right now. So again, I'll make it easier on myself and just take the leaves right now. We're going to use M and G. 2 and 2, so their summed frequency is 4. Out they go. All right, we've made progress. Now let's take the 2 least frequent nodes here, so those are going to be the 2s. We're going to combine them together into, we're going to pop them and push them back by, after combining them together into a 2 plus 2 node, which is 4. This is going to have frequency 4, all of them considered as 1. Okay, so now I've got this subtree, this subtree, this subtree, this subtree left in our priority queue. So now I'm going to take the 2 least frequent nodes. So I'll just pick these 2 because they're smaller, but I could have picked this one and this one if I wanted to. So notice that this vowel is still laying low. All right, so now I've got 4 and 3. So I'll combine, this 3 and this 4, that's easier for me. Less drawing. So here we go. Boop. And so I'll put the 3 over here. And the 4 over here. That's not enough room, is it? Here we go. Making moves. Here we go. All right. Oh no. So I'll put these together now. Bam, I have a 7 node now. Okay, so now I can pick the 2 least frequent nodes. I've got the 4 and the 5. So I'll take the 4. I'll take the 4 and the 5 node. And I've always been putting the smaller one on the left. That is technically how your book does it. I don't think it matters. Like, the left is the first one you pop, but I think it's not really going to matter. But I might be wrong there. So now I've got the 4 and the 5, and now we've got a space issue. So I'm going to start shrinking some of these. The 4 and the 5 go together. Here we go. 4 and 5, just like this. They come together into a 9 node. Boop, boop. And so suddenly we have just 2 left, a 7 and a 9, so we'll pop the 7 first, then the 9, and put the 7 on the left, just following the book's algorithm. But I think either way would have worked. Oh no. Come back. So, suddenly, 7 and 9, they come together to be of frequency 16, and oh man, that's everybody. So now that I've only got one thing left in my priority queue, there's nothing more to do. I can stop the algorithm. Okay, so we stop once we only have one thing in the priority queue. And it's a node, it's a pointer to a node that like represents this entire tree. Yeah. So the idea is we now have compressed emergency meeting into this tree. And so now if we follow all of the paths, we get optimal answers. So let's see here. These are going to be zeros. These are going to be ones. Zero, one, zero, one. And notice that everybody, just by virtue of not using all 256 characters, in the worst case, we've got length 1, 2, 3, 4. 4 bytes long. Or sorry, 4 bits long, which is a whole lot less than ASCII, which is 8 bits long. So no matter what, we've made a whole lot of progress. So it looks like the shortest thing to represent in binary form now is the E, because it appeared most often. The E is going to be 1, 0 whenever we print it out. Okay, the E is 1, 0. That's its code. Okay, the C is going to be 1, 1, 0, 0. Yeah. Dot, dot, dot. So that's the idea. It's beautiful, right? Okay, so that's the compressed form of everything. And now let's extract the lookup table from the tree. So here's our tree. It's beautiful. Let's algorithmically come up with the fact that, oh yes, E is 1, 0, C is 1, 1, 0, 0, because that is what we need to go and finally like compress the file originally. I'm going to try real hard to, nope, that won't work. Come back. Let's see if I can shrink it after I do this. Yeah, there we go. Beautiful. I missed a 1, it seems. Sorry. Okay, so now we're just going to run the algorithm in the book again. So this is the make the Huffman tree, Huffman build tree. And now we're going to program on paper. We're going to execute Huffman get codes. So the idea is it's a recursive algorithm that keeps track of like how much, what node it's at in the subtree, what the prefix so far is. So like once it's here, it knows that the prefix to either of these two nodes, either of its two children, is 0, 0. We have to keep track of that as a parameter. And then, yeah, once we get to a leaf, we just output it. So the way that this is going to work recursively, so recursively, we're gonna like start here, start at the root of this tree / try, and we're gonna say that our prefix is, I'll put this in purple for prefix. Our prefix is empty at the beginning. And if you just follow this algorithm, then if you're a leaf, you're going to do one thing. That's the base case. You're going to print out the prefix. Otherwise, you're going to recurse left and right, adding 0 if you recurse left to your prefix, and adding 1 to your prefix if you recursed right. That's the idea. And eventually, once you hit the leaves, you'll have stored up the prefix that is like their actual encoding. Okay, so here we have the prefix of 0. Here we have the prefix of 1 when we make the recursive call. And then here we have the prefix of 1, 0. Here we have the prefix of 1, 1. And so naturally, these are all going to like, even down here, we're going to have 0, 0, 0. And so this one down here, 0, 0, 0, 0, will be its prefix. We know it's a leaf, so that is its final encoding. We're going to be like, okay, yes, R is 0, 0, 0, 0. Okay? So R is encoded to be 0, 0, 0, 0. 4 zeros. Okay? That's the idea. So once you get to a leaf, prefix at that point is the encoding for that character. And so now, emergency meeting in binary is now, well, the E, where is that? It's over here, it's 1, 0. It's 1, 0. I'm going to use spaces, but obviously there are no real spaces in binary. M is, where did that go? It's over here, it's 0, 1, 0. Another E, so 1, 0. Now an R, 0, 0, 0, 0. A G, 0, 1, 1. And you can keep on doing this. And it's going to be a whole lot shorter than 16 times 8. Which was the original size. Okay, so we've just compressed things, and now I'm going to be very, very nice to you. This is a bit of a complicated thing to do, not in terms of implementing it, but of designing it, and so I'm going to actually walk you through your lab. I'm not going to give you everything, so you're not going to be getting this code that I'm writing today, for example, and in the next lecture, but I mean, if you just follow along with me, you're going to have a 100% lab, most likely. I might pause a little bit and have you fill in some pieces, but for the most part, I'm going to implement your lab with you. Okay, so you are welcome. Let's get started. Is there anything else that I want to talk about here before we go there? No, it's just showing you how, eventually you're going to read this, right? It's just showing you how you can go from the encoding to the final text, things like that. And yeah, that's the beauty of it all. So let me get ready to program and then I'll be right back. Okay, let's do this. So here is your lab. It's essentially this. We're going to implement Huffman coding together. So get your stuff, get ready to go, and then I'm going to walk you through what to do. All right, so assuming you have copied the starter code as I have, we've got these files. And eventually, we're just going to run compress.cpp. That's going to be the final little program. And what it's going to do is it's going to read a file. You give it a file name as one of the command line arguments, and then you either say, I want the codes for this file, or I want to actually compress the file. And so I've just made this main function for you. You don't have to worry about it. But this is what it does. It gets the file, it opens the file, and then it figures out, hey, did we want to do get the codes or compress the file, and depending on that we're going to do stuff. So we always need to build the tree, so I've made a Huffman coding class that builds the tree given a file object, and then we're going to get the codes no matter what, because either we wanted the codes themselves or we wanted to actually compress the file using the codes. So we're going to get them. I'll show you what the type is later, and then for each piece of code, we're going to, if the user chose that, hey, I want to see the table for the encoding table, we're just going to go and extract them. They're going to be pairs of pairs of characters, and then the string that represents those characters. So we're just going to print them out, the first thing and the second thing with some colons. And otherwise, if the user didn't choose codes, they chose to compress the file, we're going to compress it using a method in this Huffman coding class, which we were going to implement. Okay, that's all there. And so I've given you many a fun file like Shakespeare, of course, and like the Quick Brown Fox. These are files that you can use to compress things with, and that's what I'll be grading you on, among other things. So yeah, the first thing that we're going to do is talk about the implementation of the tree itself. So let's, there are two kinds of nodes in Huffman trees, and they hold different things: leaves and internal nodes. The leaves, as you remember, they held a character and a frequency. Okay, so a character, and a frequency. And internal nodes hold, well, they have to hold subtrees, right? They have to hold like pointers to this tree over here. This subtree, like this node right here, holds a left child, a right child, and also a frequency. Okay? And that's the idea. So what I've done is I have used the magic of inheritance to make these nodes. Okay? So everybody in the tree, every node in the tree is an H-tree node. You can consider it an H-tree node, but they will be subclasses of H-tree node. Okay, so that's the cool new thing. Because I've made this a pure, virtual destructor, which means this is an abstract class now. So I cannot instantiate an H-tree node, but I can instantiate one of its children, a leaf node or an internal node. Okay, that's the idea. So every H-tree node, it has all of these methods because we might need them. It has, obviously, we'll give them all their own constructors, but an H-tree node itself, because every node, no matter what, needs a frequency, we're going to store the frequency inside of the H-tree node class. And so it's going to be a protected frequency because we want to use it in its subclasses, so it's not going to be private. That's beautiful. And then we have a bunch of overwritable functions. So for example, we want to know whether or not our current node is a leaf or not. So we're going to implement an isLeaf method, and it's going to, the default implementation is going to have it return false. Only for leaves will it return true. Okay, we're going to implement it, we're going to override that. Okay. Also, the get frequency is just a getter. We should never need to override it, so it doesn't have to be virtual. Then, yeah, isLeaf needs to be virtual because we're going to override it in the leaf class, and then a virtual destructor because we want to do different things depending on whether or not we have pointers inside of ourselves. For example, internal nodes has those two left and right pointers in addition to the frequency that it's getting by virtue of being a subclass of H-tree node. Okay, and similarly, every leaf node holds a frequency by virtue of being a H-tree node. It gets it from there. And then also it holds a character because it is a leaf. That's the other thing that it needs to hold. Okay, so then, depending on whether or not it's a leaf, we're going to use this isLeaf method. Depending on whether or not our node is a leaf, we can either get its character, which we're going to have to override in the correct function. Right now we're going to give a default silly implementation of return -1. Or we can have a left or a right child, in which case we'll call get left and get right. And I'm going to give just a dummy implementation of those in this class as well, so that in the proper classes where left and right makes sense, where get a character makes sense, we're going to override these with the proper implementation. Okay, and we'll use isLeaf to figure out whether or not, oh, we're at a leaf. Okay, we can use get character, it's going to do the right thing. Or we're at an internal node, we can use the get left and get right to get the left and right child. Okay, I hope that makes sense. So that is that. And so now every leaf node needs to implement all this stuff. All right, so a leaf node is going to take a frequency and a character. It's going to set its frequency using the constructor for its parent class, and it'll set its character using the initializer list. And so now we need to actually override the getter, because the getter was, okay, we need to get the frequency. Oh man, oh, sorry, not get frequency. We need to override the get character function because we actually have a character to give back. Okay, so I'm going to implement this down here. Oops. So you don't say virtual anymore, but you say override. And we have a character to give back now because it's one of our private member variables. So I'm going to return the character that we're saving in this node. So for example, we were at this R node. I'm going to return back the R. Okay, if we had a pointer to that. Oops. That is, okay, cool. Okay, so that's that. We've done it. And then also, this node is a leaf, so we want to override the isLeaf method to actually return true, given a pointer to a leaf node. Boop. And this is override. Return true. This is a leaf. Okay, so that's the leaf node class, and then we're going to do the same thing for the internal nodes. The getters and setters for left and right now make sense because we're at an internal node, so we should override them to do something good, okay, to actually get the left child and the right child. Okay, so let's do that. And we're going to say override here. And instead of returning null, we're going to return our left child, or our right child. Okay, so we had a left child or a right child to return, and we're going to give them back. Okay, also, for leaf nodes, there's no pointers or anything. The destructor is trivial. There's nothing to actually go and delete, because every other thing is going to be deleted automatically. But for internal nodes, we're saving pointers, and these pointers will be made on the heap, okay? Okay, that's the idea there. So we need to remember to delete those things. And so let's go and implement our destructor now for this particular class. So internal node. Sorry, tilde, internal node. So the destructor needs to delete the left child and the right child. We need to delete the subtrees themselves, in fact. But the reason this is going to work out is because we can just say delete left, delete right. And this is actually going to do the correct thing. Remember that delete is going to call the destructor on the left child. Same for the right, okay? It's going to call its own destructor. So if that child itself was an internal node, before we're finished, it's going to delete itself using its own version of this destructor. Isn't that beautiful? It's secretly recursive. So for example, if I say, hey, delete the root of this tree, delete the 16, it's going to recursively delete this one and this one. I'll say delete left and delete right, which will call their own destructors, and this one is also in an internal node because it's not a leaf. You see that? This is itself an internal node, so it will call, before its destructor finishes, delete my left, delete my right, to recursively delete its subtrees. And eventually, it's all going to work out, okay? Which is beautiful. It's so nice. The destructor is secretly recursive, and it takes care of the deletion for you. That's super nice. And yeah, that's all I have to say about those things. We've successfully implemented all of these node classes, and that's a good place to stop for now. So let me now explain the Huffman coding class, and then I will break for the next lecture. And so the Huffman coding class is what's going to package together all these operations that we were talking about, building the tree, compressing stuff, getting back the codes and things. So the constructor is going to take the file that we want to compress. Okay? All right? So it's going to take the file that we want to compress, and it will build the frequency table and things like that. It's going to build the tree for us. Okay, so the two things that we store inside of our Huffman coding table is going to be our character frequency table, which is a hash table. It's an unordered map from characters to their frequencies, so ints, and then we are also going to store the root of our H-tree node. Okay? That's the idea. And that will store like the very top thing that we can use to follow and get our codes. That's the idea. So that's the tree root. We're going to save that. We're going to build it up inside of our constructor. It's going to build the tree, okay? Which involves making the frequency table, setting this tree root, things like that. So that is, in essence, the .h file, which you're technically not going to turn in anyway. That's the idea. And what you will be turning in is the implementation of the .cpp file, and so we've got a long way to go there. Okay, so that is going to be the topic of the next lecture then. So I will see you in there, and we will continue with this.